These are the answers to homework 3I. Here's the one definition for you to know. Now to the questions. Question number 1 asks to calculate the vapor pressure of each of the following solutions at 21 degrees Celsius if the vapor pressure of pure water is 18.7 torr at 21 degrees Celsius. The colligative property of vapor pressure lowering states that if you dissolve a non-volatile solute in a liquid, you will cause its vapor pressure to decrease. So we would expect that if you dissolve in A, urea, or B, magnesium chloride in water, you're going to cause water's vapor pressure to be lowered from its 18.7 torr value to some lower value. For question number 1, they said 0.25 moles of urea, which is a non-electrolyte, are dissolved in 9.75 moles of water. To calculate the vapor pressure of the solution, P, we're going to multiply the mole fraction of the solvent multiplied by the vapor pressure of pure solvent. It's important to recognize here that the mole fraction in this equation is the mole fraction of the solvent, not the solute, which we normally calculate. So we'll have to calculate the mole fraction of water in this urea water solution. They've given us the moles of both components. The moles of water in the solution are 9.75. The moles of urea are 0.25, so we add the two together to get the moles of solution, and this way we calculate the mole fraction of water as 0.975. The vapor pressure of the solution will therefore be the mole fraction of 0.975 multiplied by the vapor pressure of pure water when nothing is dissolved in it. Rayold's law essentially states that if the solution is really only 97.5% water, we can only expect 97.5% of its natural vapor pressure, and that's why the answer comes out 18.2. That's 97.5% of 18.7. In B, we're dissolving 0.25 moles of magnesium chloride in 9.75 moles of water, and the only difference is magnesium chloride is an electrolyte, whereas urea was a non-electrolyte. Electrolytes dissociate into ions. And so when magnesium chloride gets dissolved in water, each formula unit dissociates into one magnesium ion and two chloride ions. 1 plus 2 is 3. You get 3 solute particles for each one solute formula unit that you dissolve into the solution. So if they say there's 0.25 moles of magnesium chloride going into the solution, the actual number of solute particles will be that number multiplied by 3. So we're actually going to have 0.75 moles of solute in this particular solution. Using Rayold's law, we're going to calculate first the mole fraction of water in the solution. That'll be the 9.75 moles of water. We'll divide it by the total moles, which is the 9.75 moles of water, and now the 0.75 moles of solute particles, giving us a mole fraction of 0.9286. Using Rayold's law, we multiply the mole fraction by the vapor pressure of pure water, and we would expect the vapor pressure of this solution to be 17.4. It's lowered quite a bit more than the previous solution because electrolytes produce more solute particles, which cause a greater decrease in the solution's vapor pressure. Number 2 says calculate the vapor pressure of each of the following at 23 degrees if the vapor pressure of pure water is 21.1 at 23 degrees Celsius. In this case, they're telling us 17.6 grams of urea are dissolved in 125 grams of water. In order for us to calculate mole fractions, we're going to have to convert the grams of each of these different components into moles. So first for urea, I'll use its molar mass of 60.07 grams per mole to calculate the number of moles of urea. And for water, I'll use its molar mass of 18.02 grams per mole to determine its number of moles. Now the problem is very similar to number 1. We have the moles of the two components, and to calculate the vapor pressure of the solution, we first need to calculate the mole fraction of solvent. That's going to be the 6.937 moles of water divided by the total moles that make up the solution, giving us a mole fraction of 0.9595. Rayold's law now says multiply the mole fraction of your solvent by 21.1, and that'll give us the vapor pressure of this solution, 20.2 torr. In 2B, we're dissolving 17.6 grams of magnesium chloride in 125 grams of water. So we can calculate how many moles there are of magnesium chloride that are dissolving. Multiply or actually divide by magnesium chloride's molar mass will cause the grams to cancel out. So we're dissolving 0.1849 moles of magnesium chloride into the solution. Because it's an electrolyte and each magnesium chloride formula unit dissociates into 3 individual ions, the actual number of moles of solute particles in this electrolyte solution is always going to be more. It's going to be 3 times 0.1849, giving us 0.5546 moles. The 125 grams of water, we can determine the number of moles of that. It's the same as it was in part A, 6.938 moles. And now to do Raoult's law, we calculate the mole fraction of the solvent, which is 6.938 moles of water divided by the total moles of the solution. The mole fraction turns out to be 0.9260. Multiplying 0.9260 by the vapor pressure of pure water at this particular temperature, which is 21.1, the vapor pressure of the solution turns out to be 19.5 torr. So these are both examples of calculations to determine vapor pressures of solutions if you dissolve something non-volatile into the solvent. The solvent's the only component that evaporates, so it's the only one that's producing vapor pressure. Non-volatile solutes don't evaporate, they don't produce vapor pressure, so we're just calculating how much the vapor pressure of the solvent gets decreased. Problem number 3 is different. We're mixing pentane and hexane to form an ideal solution, and they tell you at 25 degrees Celsius, the vapor pressures of pentane and hexane are respectively 511 torr and 150 torr. Because both components have vapor pressures, that means they're both volatile. So if both components of a solution are volatile, you will actually have to calculate the vapor pressure contribution from each. And that's going to require calculating the mole fractions for each, and that's what we're going to do in part A. Part A asks you to calculate the mole fractions of the pentane and hexane in the solution. In this particular problem, they told us that we were mixing 25 milliliters of pentane with 45 milliliters of hexane. So this is volume, and somehow we have to convert this into moles in order to get a mole fraction. We saw this on our last homework assignment. If you're given the volume of some substance and you want to know how many moles there are, you first have to convert the volume into mass. And the way you do that is with a conversion factor between volume and mass, and that conversion factor is called density. And in the problem, it says pentane's density is 0.63 grams per milliliter. That means 0.63 grams of pentane equals 1 milliliter of pentane, and we can write that equality statement as a fraction with the milliliter on the bottom to make those milliliters cancel out. This will be how many grams of pentane we actually have. If you want to know the moles of pentane, you just multiply by pentane's molar mass with the gram portion on the bottom and the mole portion on the top, and we can calculate how many moles of pentane there must be in this mixture. We're going to do the same thing with the hexane. We're given its volume. It's a different substance. It has its own unique density. We'll look that up, 0.66 grams per milliliter. We'll use its density to convert the volume into mass. And then once we have the mass of hexane, we'll use hexane's molar mass to convert mass into moles. This comes out 0.345 moles. I can now add those together to get the total number of moles of the mixture. And to get the 2 mole fractions, I would just take the moles of one and divide it by the total. So for pentane, 0.218 moles over 0.563 moles gives me a mole fraction of 0.387. And if you know there's only 2 components in the mixture, the other mole fraction has to be 1 minus that, because if you have 2%, and if one of them is 38% and there's something else in there, it has to be 100 minus that, that'd be 62. So if you have 2 mole fractions and there's only 2 components in the mixture, then they have to add up to 1. So the second one would have to be 1 minus 0.387, which would be 0.613, I think. But we can do it the long way. We can actually take the moles of hexane divided by the totals and get the same answer. Either way is fine. So these are the mole fractions of both components in this particular solution. Now B says calculate the equilibrium vapor pressure of the solution. So because both the solvent and the solute both have vapor pressures, it means they're both volatile. We're going to apply Raoult's law to both of those. So first for the pentane, we're going to multiply pentane's mole fraction by its pure vapor pressure. And then for hexane, we're going to multiply its mole fraction by its pure vapor pressure. Hexane is volatile, so that's why that vapor pressure has to be added to the pentane. If the hexane wasn't volatile, this would disappear. The problem would be just like we did in questions 1 and 2 when the solute is non-volatile. But if the solute is volatile, then you add the contribution to the vapor pressure from that. Multiplying out, The vapor pressure from the pentane would be 198 torr. Notice it should be a 2 significant figure because really the 0.38 was a 2 significant figure mole fraction. And this is going to be 92, should be a 2 significant figure number because the 0.61 was 2 significant figures. Add those together, you get 290.2, but the answer, because it's an addition problem now, will have to be rounded to the tens place. So the correct equilibrium vapor pressure of this solution should be 290 torr, no bar over the zero, no decimal point. Number 4 says to consider the following 5 liquids and or solutions at 25 degrees Celsius. And the question is, place the liquids and or solutions in order of lowest vapor pressure to highest vapor pressure. So if we inspect each of these, we have pure water, which means there's nothing dissolved in it whatsoever. But if we have a 0.1 molal glucose solution or a 0.1 molal sodium chloride solution or a 0.1 molal solution calcium chloride, each of those have non-volatile particles dissolved in them. Glucose is a non-electrolyte. So if I just assume I have 1 kilogram of water, then a 1 molal solution would be 1 mole of glucose per 1 kilogram of water. In this particular problem, it's a 0.1 molal solution, so that means I would have 0.1 moles of glucose in the 1 kilogram of water. And because glucose does not ionize or dissociate, it's a non-electrolyte, we would therefore have 0.1 moles of individual solute particles in this particular solution. That's going to lower the vapor pressure of the glucose solution with respect to pure water. The sodium chloride solution would also have 0.1 moles of sodium chloride dissolved if we assume it's 1 kilogram of water. But because sodium chloride is an electrolyte, and from its formula, you should be able to see it dissociates into 2 ions per formula unit, we go 0.1 moles times 2, and have 0.2 moles of solute particles dissolved in the 1 kilogram of water. There's more non-volatile solute particles. It's going to lower the vapor pressure even than the glucose. So right now, out of the 3, pure water would have the highest vapor pressure. We dissolve 0.1 moles of a non-volatile solute into the water, the vapor pressure goes down. If we dissolve 0.2 moles of non-volatile solute particles in the solution, the vapor pressure goes down even more. And then we get to the calcium chloride solution, assuming a kilogram of water, we would have 0.1 moles of calcium chloride dissolved, but it's an electrolyte. From its formula, it dissociates into 3 ions, so 3 times 0.1 would mean 0.3 moles of solute particles dissolved in the kilogram of water. That would have the lowest vapor pressure of any of these 4. So right now, if you're ranking these from lowest to highest, the calcium chloride solution has the lowest vapor pressure, sodium chloride a little bit higher, glucose a little bit higher, water is the highest. The last solution, water with 0.1 moles of methanol dissolved in it, methanol, it says in the problem, has a vapor pressure of 143. That's a volatile component. So if that's a volatile solute, then both water and methanol will both be evaporating, contributing to the vapor pressure. And anytime you have a solution made of 2 volatile components, the vapor pressure of the solution will always be somewhere between the vapor pressure of the pure solvent and the vapor pressure of the pure solute. So water has a vapor pressure of 23.8 at this temperature, methanol 143. So a solution of methanol and water would have to have a vapor pressure between 23.8 and 143. Therefore, it's going to actually be higher than that of pure water. And so therefore, the lowest vapor pressure of all will be that of the calcium chloride solution, sodium chloride second, glucose third, and then water fourth. And then the highest vapor pressure of all will be the one with the volatile component in it, the methanol.